Let's take a look at chapter 3.3, properties of logarithms, okay? In this chapter, we're going to look at a few different properties that are going to help us in finding decimal approximations of logs using our calculator, as well as a few properties that will allow us to simplify logs and expand logs, which will later on down the road help us with solving logarithmic equations, as you'll see in the next section of the chapter. So let's start off with our change of base formulas. Some calculators only have two types of log keys, the common log and the natural log. While these are the most frequently used logarithms, you may occasionally need to evaluate logarithms with other bases. To do this, you can use the following change of base formula. Log base a of x can be rewritten as log of x divided by log of a. Or similarly, log base a of x can be rewritten as ln x divided by ln of a. All right, so log base a of x can be rewritten as a quotient of common logs. Notice these are both log base 10. Or it can be rewritten as a ratio or quotient of natural logs, the natural log of x divided by the natural log of a. So if you're using a TI-84, you may be able to change the base of the logs directly. It depends on the particular model that you have. So get out your calculator and select the math button. Okay, hit the math button and scroll down to option A. Option A will allow you to type in a log with a particular base. Now, if you don't have that option on your calculator, then you will have to use the change of base formula to evaluate the logs. And sometimes it's just easier to use the change of base formula anyways. So let's do some practice here. Use the change of base formula to evaluate the following logarithm. Round your solution to 3 decimal places. Here we have log base 3 of 8. Well, again, we can rewrite this as a ratio of common logs. This would be log of 8 divided by log of 3, or a ratio of natural logs, ln 8 divided by ln 3. And plugging either one of those into your calculator will give you a decimal approximation, 1.893. Let's now evaluate log base 4 of 25. Well, again, we can rewrite this expression as a ratio of common logs, log of 25 divided by log of 4, or a ratio of natural logs, the natural log of 25 divided by the natural log of 4. And plugging either of those into your calculator will give you out the decimal approximation, 2.322. All right, so both of these will give you the exact same thing. Again, you can rewrite this as a ratio of common logs or natural logs for your change of base formula. All right, let's look at a few other properties of logarithms. Let a be a positive number such that a does not equal 1, and let n be a real number. If u and v are positive real numbers, the following properties are true. Log base a of u times v is equal to log base a of u plus log base a of v. Similarly, the same property holds true for natural logarithms or common logarithms. Ln of u times v is equal to ln u plus ln v. What does this mean? Well, if we have a product inside of a log can be rewritten as the sum of two separate logarithms. Notice that they end up with the same base. Similarly, this property could be used in reverse as well. We could condense the sum of two separate logs into a single logarithm with a product of u and v on the inside. That is our product property. We also have a quotient property. The quotient property says log base a of u divided by v is equal to log base a of u minus log base a of v. If I have a quotient or division inside of a logarithm, I can rewrite that as the difference of two separate logs, log base a of u minus log base a of v. Or similarly, if I have the difference of two separate logarithms, I can condense that into a single logarithm by taking log base a of u divided by v. Okay, again, these properties can be used to go in either direction. And finally, we have the power property. Log base a of u raised to the nth power is equal to n times log base a of u. The power property says that if we have an exponent associated with the quantity inside of the log, here we have u raised to the nth power, we can bring that power to the front of the log as a constant multiple, n times log base a of u. Or if we have a constant multiple in front of a log, we can bring that constant multiple into the log as a power. Right? Again, these properties can be used to go in either direction depending upon which is going to be most helpful or what is being asked of you in the question. All right. Now, also, don't forget these properties from the previous section. Log base a of 1 is equal to 0. Anytime you see 1 inside of a log, always simplify it to 0 right off the bat. Also, log base a of a is equal to 1. Anytime you see log base something of the same exact quantity inside of the log, all right, always rewrite that as 1. So let's put some of these to use and see how they can help us to simplify some expressions. Find the exact value of each expression without using a calculator. Here we have log base 5 of the cubed root of 5. Think back to the properties that we had on the previous page. One thing that you should recognize is that roots can always be written as fractional exponents. In fact, a cubed root is the same thing as raising to the 1/5 power. This is the equivalent of log base 5 of 5 to the 1/3. Well, why does writing this root as a power help us? Well, now we can use the power property. All right, using the power property says that I can take this exponent and bring it to the front of the log as a constant multiple. In other words, I have 1/3 times log base 5 of 5. And now I have log base 5 of 5, and anytime I evaluate a log that has the same base as the quantity that's inside of the log, that always simplifies into 1. So this gives me 1/3 times 1, and 1/3 times 1 gives me 1/3. Let's try another. Here we have log base 2 of 4 squared times 3 to the 4th power. Notice in this case that I have two quantities inside of the log that are connected by multiplication. Well, if I have quantities inside of a log connected by multiplication, we can rewrite that as the sum of two separate logs. In other words, log base 2 of 4 squared plus log base 2 of 3 to the 4th. Now, each one of these quantities has a power associated with it. What can we do? We can use the power property. Bring each one of these powers to the front of the log as a constant multiple. This gives me 2 times log base 2 of 4 plus 4 times log base 2 of 3. Now, is there anything else that we can simplify here? Well, remember, logs represent an exponent. 2 raised to what exponent is equal to 4? Well, log base 2 of 4, that's going to simplify into 2. Remember, 2 squared is equal to 4. So that gives me 2 times 2 plus 4 log base 2 of 3. Now, 2 raised to what power gives me 3? Am I going to be able to simplify that? No. Okay, that is not going to simplify, and so our final answer here is going to be 4 plus 4 log base 2 of 3. Again, don't be afraid to have logs in a final answer, especially if the answer is supposed to be exact, okay? I don't want decimal approximations, so if you can't simplify the log, leave it as part of your final answer. Couple more here. The natural log of 1 divided by e to the 5th power. Notice that we have a quotient inside of this log. And a quotient inside of a log can be rewritten as the difference of two separate logs. In other words, the natural log of 1 minus the natural log of e raised to the 5th power. Well, here we have a 1 inside of a log. Anytime we are logging 1, that is going to become 0. Here we have a power inside of a log. Using our power property, we can bring the 5 to the front as a constant multiple. We now have 0 minus 5 times the natural log of e. And the natural log of e, as you guys know, is 1. Remember, anytime you are logging with the exact same base as the quantity inside of the log, in both of these cases is e, that is going to be 1. This is 0 minus 5 times 1, which gives me negative 5 for my final answer. All right, let's try a couple more here. Find the exact value of each expression without using a calculator. All right, well, what can we do? A couple different ways we could go about solving this one. One thing to make note of is we do have these powers inside of the logs. Well, using the power property for each of these logs, what can we do with them? We can bring them to the front as constant multiples. Now, I already have a 2 in front of this log, so I just multiply it in with the 2. 2 times 6 gives me 12. This would be 12 ln e minus 5 ln e. And we can treat these just like they are like terms. Yes, 12 ln e minus 5 ln e. Okay? And also one thing to make note of, ln of e is equal to 1. This is 12 times 1 minus 5 times 1. 12 times 1 minus 5 times 1, that gives me 7. All right? So a couple different ways that you could go about solving this one. This is just one of those methods. All right, let's take a look at one more here. Log base 5 of 75 minus log base 5 of 3. Okay, here I have two logs, and what are they connected by? They are connected by subtraction. I have a difference of logs with the same base. Sometimes it can be helpful to condense this into a single logarithm. Remember that I can take the difference of two logs and turn it into a single log with a quotient. In other words, this could be turned into log base 5 of 75 divided by 3. Well, why does that help us? 75 divided by 3. 75 divided by 3 is 25. And so this is the equivalent of log base 5 of 25. And again, recall that logs represent exponents. This is saying 5 raised to what exponent gives me 25. My answer in this case is going to be 2. All right, now the same thing could have been done over here. We also could have brought this 2 into the power. All right, bringing that 2 into the exponent would change things up a little bit here. All right, bringing that 2 into the exponent, we would have ln of e raised to the 12th. Okay, let's see if we can get this on here. All right, again, if I were to bring this down, okay, this would turn into ln e to the 12th power minus ln e to the 5th. Now I have a quotient of natural logs. All right, I could rewrite that as ln e to the 12th power over e to the 5th power. And when I divide, now this is the natural log of this entire quantity here, okay? When I divide exponential quantities of like values, I subtract the exponents. This would be ln of e. 12 minus 5 gives me 7. Now I could use my power property again, bring this 7 to the front. This would be 7 times the natural log of e, and the natural log of e, that's equal to 1. 7 times 1 gives me 7 for my final answer. So a couple different ways that you could go about solving that particular problem. All right, so there you have it, a couple uses of our properties of logarithms. In the next video, we'll do a few more problems where we are expanding and condensing our logs.